Welcome back to Software Engineering 2FA3 Discrete Mathematics with Applications 2. I am Bill Farmer, and we're going to continue discussing the topic of predicate logic. Today we're going to look at proof systems for our version of first-order logic FOL. Now, a proof system for FOL is a set of logical axioms. So logical axioms are formulas that are true or valid in every situation, and a set of rules of inference. The rules of inference are a way of inferring truths from things we already know are true, or we already have assumed are true. And we use these axioms, these logical axioms or rules of inference, for constructing proofs that show that a formula follows from a particular set of premises. So let P here, script P, let it be a proof system for FOL. And we'll say that A is a syntactic consequence of gamma. So A is a formula, gamma is a set of formulas in P, which we write like this, if there is a proof of A from gamma in P. In other words, we can prove A from gamma and the logical axioms using the rules of inference of P. Okay, so syntactic consequence is a special case of logical consequence. And we say A is a theorem in P, which we write like this. Notice there's no gamma here. If there is a proof of A from the empty set of premises. So we could have just as well written this like this. So a theorem is something we can prove without any premises. And we say that gamma is consistent if not every formula is a syntactic consequence of gamma in P. In other words, gamma is consistent if we can't prove everything from gamma. If we, and this means that we can't prove falsehoods. Normally, if in a proof system, if you can prove a falsehood, you can prove everything. So another way of saying it is gamma is consistent if it makes sense, if it doesn't embody contradictions. And we'll say that P is sound if whenever A is provable from gamma in P, that implies that A is a semantic consequence of gamma. So sound says that syntactic consequence implies semantic consequence. And we'll say P is complete whenever A is a semantic consequence of gamma. There will be a proof of A from gamma in P. So completeness says that semantic consequence implies syntactic consequence. Ideally, we'd like P to be both sound and complete. Now, if we have a theorem, a theory, and remember a theory is a signature plus a set of sentences of that signature. So if we have a theory of FOL, we'll say that A is a theorem of T in P, which we'll write like this. If A is a syntactic consequence of gamma in P, or in other words, if we can prove A from gamma in P. Okay, so I have a question for you. What is the simplest proof system for FOL that is sound? I'll give you a moment to think about that. Okay, so let me remind you, a proof system is sound if syntactic consequence implies semantic consequence. So the simplest proof system, so it is a proof system that can't prove anything. And how do we get such a proof system? we just have a proof system that has no logical axioms, no rules of inference. It can't prove anything. So this is never true. And so that means the whole statement will be true, because we can't prove or I should say anything we can prove must be a logical consequence, but we can't prove anything. So that means everything we can prove actually will be a logical consequence, because we can't prove anything. So the simplest proof system that is sound is just a proof system that can't prove anything. It'll be a useless proof system. So I have another question. This is about completeness. What is the simplest proof system for FOL that is complete? I'll give you a moment to think about this. Well, let's go back. Completeness says that semantic consequence implies syntactic consequence. The simplest thing is to make sure that we can prove everything. Because we can prove everything, that would mean certainly, if we can prove everything, certainly we can prove semantic consequences. So the answer for this is it is a proof system that can prove everything. So that's a very simple, complete proof system. And again, just like our simple proof system that can't prove anything, this is a proof system that can prove everything. It's pretty much a useless proof system, but it is complete. Okay, so there's many kinds of proof systems for first-order logic. I mentioned some of the main ones and the people who have developed these. The first kind, the Hilbert system, we can think of as being a particularly simple system. These two, natural deduction, sequent, are very natural and practical systems. And these two, semantic, tableau, and resolution, these are refutation systems. What that means, instead of proving a formula, we refute the negation of the formula. Basically, we show that if we have the negation formula, we can derive a contradiction. Now we're going to talk today about Hilbert-style proof systems. These proof systems were proposed, as I mentioned above here, by Frege and Hilbert. We now call them Hilbert-style proof systems. I want to mention something about Hilbert. Hilbert lived in the end of was born in the end of grew up in the end of the 19th century and lived into the 20th century. And he was very concerned about providing a solid foundation for mathematics. And he developed a program which we call today Hilbert's program, which is based on using formal proofs to put mathematics on a solid foundation. And when Hilbert lived, he was really the most important, the most influential mathematician in the world, I would say. And he died during World War II, and basically he suffered greatly under the German Nazi regime, because his university at Göttingen, which was one of the leading, maybe the leading places to study mathematics and physics in the world, his department was gutted by the Nazis. They basically made all people who were of Jewish heritage or related to people of Jewish heritage lost their jobs, and a great many of these people went to the United States, and this resulted in an amazing shift of mathematical intellectual power from Germany to the United States right before World War II started. So what is a Hilbert-style proof system? Well, if we have L as a logic and A as a formula of L and gamma is a set of formulas of L. A Hilbert-style proof system consists of a set of formulas of L that serve as the logical axioms and a set of rules of inference. So that part is like other proof systems. What's different is a proof of A from gamma and P is about as simple as can be. It's just a finite sequence of formulas that ends with A, such that every formula in the sequence is either one of the logical axioms of the proof system, member of gamma, or is inferred from previous formulas in the sequence by one of the rules of inference of P. So we can think of a proof as just a sequence of formulas. The last formula is A. Each formula is either one of the logical axioms of P, or it's a member of gamma, or it's inferred from previous formulas. So this could be an axiom, this could be an axiom, this could be a member of gamma, and this could be inferred from using one of the rules of inference, let's say from B1 and B3. So the idea of what a proof is in a Hilbert-style system is very simple. Okay, so here's a Hilbert-style proof system for a signature of FOL. So we get a slightly different proof system for each signature. The axioms of H are going to be all formulas of sigma of one of the following forms. So for propositional logic, we have these three forms. So basically, these are what are called actually axiom schemas, because they are really infinite collections of formulas. So A, B, and C can be any formulas whatsoever. And we have two of these for quantification. We have one in which you can push universal quantification past or into the second part of an implication if X is not free in A. And we have another one which is called, this is called universal instantiation. We say that a universal formula implies every instance of that will replace the variable that's being universally quantified x by any term, provided that term is a term of sigma that is free for x and a. In other words, as long we can substitute for x any term as long as we don't get variable captures. Now, we also need a bunch of axioms for equality. These are the axioms for an equivalence relation. And these are the axioms for a congruence. The importance of a congruence is because of these axioms, it means we can always substitute equals for equals. If we know that A and B are equal, we can replace A with B without changing the value of the formula we start with. So notice, basically this says that if we apply a function symbol to a bunch of arguments, we apply a function symbol to the same arguments, and these arguments match up by being equal, x1 equals x, y1, and so forth, then the two applications will equal each other. And we have a similar kind of axioms for predicate symbols. Then for rules of inference, we just have two rules of inference. If we know A and we know A implies B, then we can infer B. And if we know A, we can infer for all x A, for any x. So the idea here is if we have basically proven A with an arbitrary variable x, then we can infer for all x of A. Okay, so what I want to do now is to show you an example of a proof of A implies A in H where we have no premises. So I'm going to prove this. So basically this is going to be a theorem of H. I'm going to prove without premises. So I start with, remember, a Hilbert-style proof system is just a sequence of formulas, and the last thing is what we want to prove. And so if you look at this, we can think of this playing the role of A, this playing the role of B and C. Here's A again, here's B, here's A, here's C. And if you take a moment, this is an instance of this formula, A2. A implies B implies C. That whole thing implies A implies B. That thing implies A implies C. So that's what we have here. So this is an instance of this. And this A plays the role of A, this part plays the role of B, and this plays the role of A. That is an instance of A1. A implies B implies A. So far so good. Then using modus ponens, we have, let me erase some of this. We have this thing is the same as this. So we have something like x implies y, and we have x. So with modus ponens, actually the way I should have written this is, instead of 1 and 2, it should be 2 and 1. So with modus ponens, we get this conclusion, which is right here. And then from A1, I can get another instance. I have A, remember A1 is A implies B implies A. So B plays the role of A. And then from modus ponens, again, we can use this with this. And again, I should have had this 4 and 3. And we get this. I'm going to just remind you that the way I wrote modus ponens is the left-hand side of an implication, then the implication, and we infer the right-hand side. So this is interesting to prove something very trivial. It took a somewhat complicated proof, and this is a characteristic of Hilbert-style proof systems. So here are some meta-theorems about Hilbert-style proof systems. So meta-theorems are not the theorems we prove in the system, but they're theorems outside of the system we prove about the system. So let sigma just be a signature of FOL. A and B are formulas of sigma, and gamma is a set of formulas of sigma. Well, there's generalization with premises. The rule that we have up here, that we can infer for all x of A from A, doesn't actually hold as stated if we have premises. So we need we can prove that we need a slightly different rule if we have A is provable from gamma in H, then we can infer for all x A from gamma in H if x is not free in gamma. So we have this side condition that has to be checked. Then we have some important theorems, a deduction theorem. If we can prove B from gamma with A, then we can prove A implies B from gamma. This theorem is very important. You'll see in a moment why this is important. And then we have the soundness theorem. It says syntactic consequence implies semantic consequence, and completeness says semantic consequence implies syntactic consequence. So H is both sound and complete, and we can put these together and prove a second form of soundness and completeness, which says that gamma is consistent in H. That means we can't prove everything, if and only if gamma is satisfiable, if and only if it has a model. And then there's a very useful theorem called the compactness theorem. It says if gamma is finitely satisfiable, then it's satisfiable. So finitely satisfiable means every finite subset of gamma has a model. So this is really only important when gamma is infinite. So if gamma is infinite and we can show every finite subset of gamma has a model, then gamma must have a model. So these are all very important meta-theorems of H. I want to conclude today with some comments about H. H is very easy to understand. This is its virtue. But it's exceedingly difficult to construct proofs in H without software support. It's really useless if you're going to construct proofs by hand. So what people do, instead of constructing a proof of a formula in H, one usually shows instead that there is a proof of A in H. So the idea is you don't actually exhibit the proof. The proof is too complicated to exhibit. You just exhibit an argument that shows it exists. And the key for doing this is a deduction theorem. So in fact, it's critical for doing this. So let's say, so you just saw a proof of this. A implies A, where A is any formula. Right here it is. I can prove it very straightforwardly with the deduction theorem. I start with an assumption, one assumption A, and it's trivial that if A is a premise, then I can prove A. Because remember, in a proof, any member of the proof can be a premise. So we get this trivially, and then we use the deduction theorem applied to one, and we get A implies A. So we haven't produced a proof of A implies A, but we've shown that if we can prove this, which is trivial, here's the proof. There's just one member, it's A. So we can show there's a proof of that, that's trivial. And then once we know there's a proof of that, we know there's going to be a proof of this by the deduction theorem. So in summary, H is much more useful for theoretical purposes than for practical purposes. And next time we're going to look at Gensen-style proof systems, which are much more practical than Hilbert-style systems, but they're a bit more complicated. Okay, we'll stop here. See you next time.